So in this video, we're going to see a new property called compactness. Actually, it's not going to be so new. It's going to turn out by the end of this video that this new definition, which looks a little unwieldy, is exactly equivalent to being both closed and bounded. We're going to introduce an alternative to this because sometimes the alternatives are easier to use, and of course, in preparation for later parts of the course and future courses, where compactness is going to be easier to use than these other definitions. So before we can say what it means for a set to be compact, we need a new definition for an open cover. So an open cover of a set A contained in Rd is a collection, U alpha, of open sets that satisfies A being contained in the union of all of those sets. So we can draw a picture, right? If I have a set A over there, then an open cover might look like this, right? You take all of these blue open balls, and you put enough of them that you've contained your entire set A. And of course, in the definition, we don't have to be very efficient, right? So the open cover can also contain a whole bunch of balls that are very, very far away from A, or it can even have one ball in it that covers all of A all by itself, right? We don't have any conditions along those lines. We just have to cover A with a bunch of open sets. They also don't have to be balls. Balls are just easier to draw. So what are some more concrete examples? The open set, the open interval from 0 to 1 is contained in the union of 1 over n, comma 1 minus 1 over n over n in the naturals. But of course, we don't have to be this efficient. The interval 0, 1 is also contained in this ridiculously large interval. Okay, so both of these are open covers. This one, of course, is a little silly. This one is sort of exact. That is, these sets are actually equal to each other. Okay, but both of them are fine. We say that a set is compact if every open cover has a finite subcover. That is, if I ever have an open cover, then I can take a subset of the cover, of which is finite, and still cover the entire set. Okay. So what's sort of an example there when that works? Well, sort of hard to figure out what does it mean to say for every open cover I can find a finite subcover, but it's certainly easy to find in many cases what a finite subcover might look like. So if I have, a bunch of balls that look sort of like this, and I'm interested in covering this little bit of the interval, then of course I can just throw away all of the balls that don't intersect the interval, and I've just been drawing them, so of course that collection is finite, and it still covers. You can imagine, in this particular situation, to be perhaps a little bit less silly, that I have the closed interval for 0, 1, and I draw a little ball around, say, every point of the form constant over 10, or constant is in the integers. Right? So I draw balls that sort of look like that. And even though I'm only drawing finitely many of them, of course, they're infinitely many balls. And for my finite subcover, I'm just going to ignore all balls, except for the ones in that little window. Okay, so there are lots of situations where you can find a finite subcover, and there are a couple of general theorems we could prove. If you have any finite set, the finite set is always compact, so we're going to prove that really rather than just doing a picture. I'm going to say, consider some cover of the finite set by an open set, by a collection of open sets ui. Then for all j between 1 and n, there exists some I depending on j, so that aj is contained in u sub ij. That's just what it means for this collection here to be a cover, right? That is, every point in my set has to be contained in some element of the cover, and I'm just giving some notation to that fact. And so that immediately gives me an open subcover, which is u sub I of 1, u sub I of 2, dot, 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 u sub I of n. Right? So what does that look like in pictures? So I have a finite set here, and I have a cover, and of course every element of that finite set has to be contained in some open set. And so I just choose a representative open set, and that's going to give me a finite cover. On the other hand, there are situations where we don't have a finite subcover, and we don't have a compact set. So the first one is the natural numbers. So those aren't finite, those aren't compact. And actually proving non-compactness is sometimes more annoying than proving compactness, because we actually have to find an open cover that does not have any sort of finite subcover. So what's such an open cover for the naturals? Well, I can draw the naturals. And my open cover is going to be obtained by just drawing a small ball of radius 1 over 10 around every point. And it's straightforward to see that actually you can't throw out any of those balls, right? Every point is covered by exactly one ball, and so there's no subcover which contains all of the naturals. Another way to have no open subcover is to look at the open interval from 0 to 1. Now that's going to be a little bit trickier because, of course, a lot of open covers will have finite subcovers, so we have to be a little bit more careful here. So in this case, we're going to do the following. We have the interval from 0 to 1, and we're going to approximate it by actually a growing sequence of sets of the form 1 over n to 1 minus 1 over n. So first of all, we just have a point, then we have sort of that interval, then we have that slightly bigger interval, and so on and so forth. And you can see that, of course, this really is a cover. That is, every point in the open interval from 0 to 1 is going to be contained in actually all but finitely many of these intervals. On the other hand, I'm going to claim that there's no possible way that you can have an open subcover. I'm not going to give a really careful proof or a very formal proof, but I'll at least give a little sketch. What would happen if you did have a finite subcover based on this initial cover? Well, these are actually nested sets. So any finite subcover is going to look like the interval from 1 over capital N to 1 minus 1 over capital N for some particular number n, right? And in particular, that cover is not going to contain the point 1 over 2n, which is in the interval 0, 1. So that's basically the obstacle, and you can expand that for yourself if it's not 100% clear, and it's sort of maybe a useful exercise. Okay, I'm going to assume that you've paused and checked for yourself that that's really true, and now I'm going to move forward to the main proof in this section called the Heine-Burrell theorem, which tells you exactly when a set is compact. And it's sort of a funny-looking theorem. It says that a set is compact if and only if the set is both closed and bounded. All right, so before I get into the proof, of course, we might groan for a second, because we already had perfectly good definitions for closed sets and perfectly good definitions for bounded sets, and they're fairly simple definitions. And then we introduce this new idea of compactness, which looks sort of crazy. It's all about infinite covers by open sets having finite subcovers, and it's sort of annoying to check. And why did we bother doing that when we have perfectly good definitions which turn out to be equivalent? We're not really going to get to that in this video, but maybe looking ahead a little bit, it turns out that sometimes actually the compactness definition is going to be a better definition for a whole lot of other situations which aren't just RD. So that's in some sense the real reason to do it. At some point we're doing analysis on other sets, and we want a better definition than closed and bounded. Another reason, which is maybe going to be something we see more sort of sooner in this course, is that it's sort of an equivalent way of talking about closed and boundedness, which is not obviously equivalent, and so sometimes the new definition really will be more convenient to work with. That might seem a little bit surprising at the moment, but I swear it's really true, and we'll see some examples. All right, with that motivation out of the way, let's do the proof. So there are going to be 4 parts. The first thing is that if A is compact, we want to check that it's closed, we want to check that it's bounded, and then we want to go the other direction. If A is closed and bounded, we want to check that it's compact. So the first direction, if it's A is compact, then it's bounded, that one's pretty easy. So what we have to do is we have to use compactness. So in particular, we better find some cover which is useful. And so here's the cover I'm going to choose. The set A is contained in RD, obviously, which is contained in this union of balls of radius n around 0, right? That's sort of clear. We can sort of draw the sequence of growing balls. And if I take the union of all of those balls, I'm actually going to hit all of RD. So that means that A is actually sitting inside of that big union. Well, that's an open cover of A, which means it has a finite subcover of this form here. And so in particular, A is contained in the ball of radius, well, the maximum of the points of the values that show up here around the point 0, and in particular, A is bounded. So boundedness, there's not a whole lot to do. Okay. The next 2 parts of the proof require a little bit more effort, and I'm going to try to say the main trick before I get into the details. It's not such a crazy idea for you to try to pause the video as you go and see if you can try to guess some of the proof once you've seen the main trick, just to see how things are going to be going. So we want to get closedness, and we need to use the fact that A is compact, which means we need to have, in some sense, some open cover that we're going to be interested in. And so let's draw the picture. We're going to be talking, we want to check that A is closed. And so when we talk about closure, what that really means is that the complement is going to be open, right? That's what it means for a set to be closed. And so that means in particular, the only property that we have for open sets is that if I choose some point x, which is outside of A, there's going to be a little ball around x that has no intersection with A at all. So that's what we want to check. So let's draw the picture. We have our set A, we have our point x, which is outside of A, and we want to check that there's a little ball there. How are we going to do that? Well, the ball is supposed to separate x from A itself, and that's hard to do. But it's easy to separate x from any individual point y in A. And how do we do that? Well, we're just going to draw, the line, for example, halfway between x and y, or maybe even sort of closer, 3/4 of the way from y to x. And we can draw that little line, and that's going to separate x from y, and it's going to give us some open set here. And more importantly, it's going to give us a closed set here, the complement of which is open and contains y. Okay, let's say all of that again to talk about the main trick, or you can skip ahead to get to the details of the proof. We want to check that A is in fact closed, using the fact that A is compact. Now, to say that A is closed is really to say that A complement is open, so that's really the thing I want to talk about. And so to check that A complement is open, what I have to do is choose some point x that's in A complement and find some little ball around x that has no intersection with A. Now that's hard to do, but there's something that's easier to do. If there's some point y that's sitting in x, I can draw easily a little box around x that contains x but doesn't contain y. And furthermore, I can make this a closed box, and then I can take the complement of that box. I'm going to scribble over my original drawing. Oops. And the complement of that box is this huge set that's open and contains y and doesn't contain x. And so it turns out that's going to be the key idea. I can separate x and y, and in particular, I can separate x and y and use either open or closed sets. And we're going to use that to actually prove the theorem. Okay, so let's do it. So I want to check that A is closed, so I want to check that A complement is open, so I'm going to fix some point x which is not in A. And for every y that's in A, I'm going to define r sub y just to be 1/4 of the distance from x to y. And we notice that the union of the balls of radius r sub y around y is an open cover of A. It's sort of a silly open cover, right? Because actually, I'm taking union of I have these balls of some radius around y. I just need actually the single point y to cover there, right? It's a really extremely large open cover of A, at least when A is uncountable. Okay, but it's certainly an open cover, and that means it actually has a finite subcover. So there's some subset of which I'll call capital Y of A, which is finite, so that A is actually contained in this finite union of balls. And I'm going to let little r be the minimum of the ry's, but only over that finite set. And so in particular, this little r is positive. So this is sort of where I use compactness in a key way. I get a finite subcover, so when I take the minimum, I end up with a number that's strictly positive. Then the ball of radius r around x intersect with A is contained in, well, the union of the ball of radius r around x intersect the ball of radius r sub y around y for all of the y's in my index set y. But that thing, of course, is exactly the empty set for every particular little y, because that's exactly how we chose these ry's, so that intersection would be empty. Okay, so what have we shown at this point? We've shown for any particular x in A, there exists some r, so the intersection of the ball of radius r around x with A is the empty set. And that's exactly what it means for A complement to be open, which is exactly what it means for A itself to be closed. So we're actually done. So we've done one direction in the proof of the Heine-Burrell theorem. Now we're going to do the more annoying direction. So we're going to assume that A is closed and bounded and prove that it's compact. And we're going to use a proof by contradiction. So we're going to assume that there exists some particular open cover, which I've written down here, that doesn't have any finite subcover. Okay. Before getting to the proof, which is fairly long, I want to talk about the two main ideas in the trick. The first of which is probably pretty familiar to you. It's a subdivision trick that we used to prove Bolzano-Weierstrass, and which was also used to prove that monotone sequences have limits. So here's the idea. Since A is bounded, we can draw some box around A. And A is bad, that is, it's not compact, that is, for this particular open cover, there's no finite subcover. And what we're going to do is we're going to chop up our box into 4 equal parts. And we're going to look at the intersection of A with each of those parts. So maybe I'll look in particular at this blue region here. And we're going to notice the following thing. Let's assume that the intersection of A with that box, that is this blue region, itself has a finite subcover of this cover here. If that were true, and also this region had a finite subcover of the original cover, and this region had a finite subcover, and this region also had a finite subcover, well, each of those 4 regions would have a finite subcover, and so the union of those 4 things would be a finite cover of the entire set A, which isn't possible by our assumption. And so, in fact, at least one of these boxes, that is, one of these regions, must not have a finite subcover. So, okay, we can assume it's this one up here. And we can keep on playing that game. We've checked that that little part of A has no finite subcover, and so we can split it into 4 parts as well. And we're going to see, well, at least one of those 4 parts also has to have no finite subcover. And we can keep on going, and as long as we split it into a finite number of parts each time, one of these tiny, tiny boxes must still have no finite subcover. Okay, in particular, sorry, the tiny box intersect with A must have no finite subcover. So that's the first trick. And so what we're doing essentially there is we're going from a big set A to this sort of sequence of arbitrarily small shrinking sets, which have the same bad property that they have no finite subcover. All right, how are we going to take advantage of that? Well, we're going to zoom in this picture in sort of this little bad region. It's going to look pretty similar to the whole thing because we're doing all of this subdivision. And when we zoom in this sort of way, we can look at some little point which is sitting in here. And if we can check that there's a point which is in those boxes, those tiny boxes, then in fact that point has to be in some element U sub I of my original cover. Now, since these boxes are getting very, very small, what we're going to show happens eventually is that one of these UIs is actually going to cover an entire box. Okay, so I haven't done that yet, and there's some work to do to check that that really happens, but hopefully you can believe me, right? These boxes are getting tinier and tinier and tinier, and so eventually one of them is going to get swallowed up entirely by an element UI. But as soon as that happens, we know that, of course, this tiny box does have a finite subcover. It's this whole region UI, right? It's a subcover of size 1. So that's going to be the contradiction that we get. Okay, so that's sort of a quick overview of the proof. If that made sense to you, it's probably not a terrible idea to pause the video for a second and try to check for yourself. Can you make these 2 steps rigorous? It's good practice to try. But in any case, I assume that you've either done that or you've decided you're not interested in doing that, and I'll keep on going and give the proof with some notation. So A is bounded, so we can draw, like I said, that A is inside of a box. Now, it's hard to draw in high dimensions, so I'm just drawing it in R2, but in any case, the box is either a box or a cube or a hypercube of some finite side length m. And then we're going to consider subdivisions of the box into 4 parts, or in general in d dimensions into 2 to the d parts, but I need to keep drawing in 2 dimensions, exactly as I was describing a few moments ago. And we make the following observation. Let's assume that A intersect the first box, B1, and A intersect B2, the second box, and A intersect B3, the third box, A intersect B4, all have finite subcovers of my original bad open cover. If that were true, then the union of those 4 finite subcovers would in fact be a finite subcover of A, and we know that that doesn't exist by our assumption. Okay, so now we can zoom in, and we're going into the sort of individual box, which doesn't have a finite subcover, and we're going to do the same thing. We're going to divide it into 4 parts. This time we're 2 to the d parts, this time with side length m over 4. And again, the intersection of one of those boxes with A must fail to have a finite subcover. And so we're going to repeat this. And if we keep on going, we're going to end up with a sequence of nested boxes, B1 containing B2 containing B3, ... with the following properties. First of all, B sub n has side length m times 2 to the n. Okay, so that part's sort of clear. That's how we've constructed the boxes at each level. And then second of all, Bn intersect A has no finite subcover, okay, of the particular bad cover, Ui that I started with. So I've done the sort of the sort of zooming in trick, and I have this infinite sequence of nested boxes, which gets smaller and smaller and smaller. Now I need to somehow take advantage of this, and in particular find my set UI, which I described here, which is going to actually contain some of those boxes. Now I don't have a lot of ways to find a UI. And what I'm going to have to do is not look at these boxes themselves, but look for individual points. So let's do that. I'm going to choose a sequence xn in such a way that x sub n itself is always inside of bn intersect a. And definitely this sort of xn exists because bn intersect a doesn't even have a finite subcover. So certainly it's not empty, right? If bn intersect a were empty, then it would have, well, a really boring finite subcover, right? We just not need to include anything. So this sequence really exists. And it's clearly Cauchy. Okay, whenever a mathematician says clearly, you should be a little bit suspicious, but I'm not going to prove that here. If that's obvious to you, then that's fantastic. If it's not obvious to you, you should try to prove it for yourself for a few minutes now, or go open up the lecture notes where there are full details. In any case, moving right along, that sequence really is Cauchy, and so we know that in fact xn converges, or rather xn itself converges to some point x. And since A is closed and xn is sitting inside of A, in fact, x has to be in A as well. So that's good. So we've gotten from these nested boxes to an actual convergent sequence. So that's sort of nice. But what are we actually going to do with the point x in A? Well, the point x in A is going to give us our set UI. Since x is sitting in A, and UI is giving us an open cover, there actually has to be some element of the open cover that contains x, right? It's an open cover of all of A, so actually it has to contain x. But since x is sitting inside of an open set, that means that there's some number r greater than 0, so that an entire ball of radius r is sitting inside of UI, right? But that's good, because remember, that means that UI, that we can draw sort of the following picture. We have x down here, and there's some ball that's around x, which is entirely sitting inside of UI. On the other hand, if we look at our picture and we sort of zoomed in, when we were doing our subdivision trick, these little subdivisions were getting smaller and smaller and smaller, and as you can see here, they're eventually actually going to have to be entirely contained in that big circle which is contained inside of UI. And in particular, for all n bigger than, well, this expression that I've just written down here, bn is sitting inside of UI. Okay, great. What does that mean? Well, bn is sitting inside of UI. That means in particular that there exists a finite subcover of all of bn, right? UI is just one element, so that's definitely a finite subcover. And that means that UI is also a finite subcover of bn intersect A. But here, we had already seen that bn intersect A has no finite subcover. So this statement here, which I've circled in blue, and this statement here are in contradiction. And so we found exactly what we wanted, which is that this assumption can't in fact be true, and so in fact A really is compact. So that's the proof. It's fairly long, but I think there are sort of two main steps, and hopefully that's sort of enough that one can try to remember most of it without remembering all of the lengthy details. Okay, now Boussoldt-Weierstrass is sort of the key result relating to this new definition of compactness, but it's helpful to do a little bit of cleanup and talk about a couple of other relationships. And there's one other definition that usually comes along with the definition of compactness I just gave, which is called sequential compactness. So I'm just going to state the definition. A set K is sequentially compact if every sequence in K has an accumulation point in K. All right, well, I don't really like thinking about accumulation points, so there's an equivalent definition. K is sequentially compact if every sequence in K has a convergent subsequence that converges to a point in K itself. Okay, great. So this is another thing which has compact in its title, as you can read ahead in the theorem immediately following. It turns out that sequential compactness is equivalent to compactness, which, as we've already seen, is equivalent to being closed and bounded. So I have sort of three definitions which all are really saying the same thing, but which don't look like they're saying the same thing. And so that's a useful thing to have in mathematics because we get to choose whichever definition is most convenient. All right, so I have this theorem here. I'm not going to give all of the details here because I think they're sort of less interesting than the proof of the Heine-Burrell theorem. We've just watched a very long proof a few moments ago. I'm just going to give a little bit of a sketch, and you can follow up yourself in the lecture notes if you'd like to see all of the details. So I'd like to check that the following statements are equivalent. K is compact, K is sequentially compact, and K is closed and bounded. So the equivalence of A and C, well, that's exactly the Heine-Burrell theorem, right? The equivalence of compactness and being closed and bounded. So I just have to check that these are related to B. So if I will go from C to B, that is closed and bounded to sequentially compact, that's actually basically the Boltzmann-Weierstrass theorem. Okay, you have to dot a few I's and cross a few T's, but it's really almost a one-liner. Okay. So the last step is to check that B implies C. That is, if K is sequentially compact, then it's both closed and bounded. And we're going to prove this by contradiction. First, we're going to assume that K is sequentially compact, but not closed. So what do? We're going to have to find a bad sequence, right? That's how we check that something isn't sequentially compact. Now, since K is not closed, we've already established earlier in the course, that means that there's some sequence xn which is entirely contained within K, which converges to a point x that's not in K. That means that every subsequence of xn is also going to converge to the same point x, which is not in K. And so in particular, that means K can't possibly be sequentially compact. Proving boundedness is similarly simple, I think. So we're going to assume that we have a set K that isn't bounded, but which is sequentially compact. And what we're going to do is there's going to be a sequence xn, so that xn is not contained in the ball of radius, say n, around 0. So in particular, the norm of x is going to diverge to infinity. And so any sequence of that form can't possibly converge to something, and indeed any subsequence is going to have this property as well, so it can't possibly converge. So we have all subsequences don't converge to any limit, and so in particular that means that K can't possibly be sequentially compact in that situation either. So we've derived a contradiction in both situations, so indeed K must be both closed and bounded if it's sequentially compact. All right, thanks.